Let's see, we stopped here. Okay, KCL, series connections, and then parallel connections. And then we'll go into KVL. Let's take series connections first. Now, the only components we study in this course are two terminal elements: capacitors, inductors, and resistors. They have two terminals each, and those are the only elements we study. Three terminal elements like transistors is for next follow-on course, which is EE 321, but not in this class. So if you have two elements, A and B, and both of those are two terminal elements, meaning they each have two hands or two terminals for making connections. If they have one terminal connected to the one terminal of the other element, we say that those two elements are in series between the outer two terminals. Okay. And simply stated, for two elements to be in series, they have to have one connection with each other. That connection point or that junction point is known as a node, N-O-D-E, node. And that node cannot have more than two connections. Here we see A and B are connected to each other. It forms a junction, it forms an electrical node, and it only has two connections, right? That node has one connection going to A and a second connection going to B. If you have a third connection or more than two connections at any node, then they are no longer in series. There are exceptions to that statement. We'll look at that exception when when a time comes with an example. So A and B are in series. If you have a third connection, that is no longer in series. You can have infinite elements connected together as long as they maintain that requirement. All the way to infinity, you would say that they are all in series. Okay. Anyone ever work with old holiday lights, Christmas lights, holiday lights, right? You have a number of light bulbs, and the reason it's called series lights is because it's electrically connected as series. So you have multiple light bulbs. Depending on how long you want it, they design it to have like 10, 15, 20, 50, 100 lights in there, 100 light bulbs, which you would then take and plug it into a power outlet. The power outlet is an open circuit connection. No current flows through a power outlet until and unless you plug something in which provides a closed loop pathway for the current to flow through. Once you take the series connection of lights and you plug it into a power outlet, current can now flow through. It flows through the lamp. Sorry, the first light bulb goes through all of them and back into the wall outlet, thus providing a closed pathway. The reason I said old holiday lights is because most modern lights do not function exactly the same way. If one light bulb in this goes out, the entire series of lights goes off, right? Anyone ever experienced that? Again, as I said, those were the older kinds, the older designs, simpler designs. You simply have one light bulb connected to the next one with one connection each. Current flows through because it has a closed pathway. If one light bulb goes out, it becomes an open circuit. The switch is now open. Current does not have a path to to flow through anymore. It's an open circuit, no current flowing, all light bulbs are off. That's the reason. So that is a series connection of elements. Easy enough, right? A parallel connection works the same way, except the requirement is that they're holding hands. That's what I like to call it, holding hands. If you have two or more elements all connected by their respective terminals to each other, and the number could go to infinity, they are said to be in parallel with each other. Okay, they're all in parallel with each other. Similar to series, you can have infinite number of elements in parallel. Most common example that you have used, I'm pretty certain everyone has used this, is your power extension strip. You see a power extension strip that you plug into the wall. A wall has one outlet. Your extension strip might have 4, 5, 6, or even 7 outlets. If you open up the back panel, which is not difficult to do, there are 2 screws. Pop out those 2 screws, unscrew them, take out the panel. You will see that there are 3 wires coming from the wall outlet. You have a 3-prong outlet, right? 3 wires for those 3 prongs, and throughout the entire strip, you will just see 3 wires going across it. And each socket is connected to those respective wires. They're all in parallel. So again, we are talking about 2 terminal elements, but a real life example would be a power extension strip, which has 3 terminals. All 3 of them are connected to each other by their respective terminals. And they're all said to be in parallel. So all you're doing is you're taking your wall outlet and you're splitting it up in parallel across, 3, 4, 5, 6, 7 outlets or more. Anyone ever seen that? The inside of a power strip? If you have one disconnected from the wall, unscrew it, take a look at the back panel. You'll see 3 lines or 3 wires just going through it. Okay, don't do it while it's live. Coming back to the example of the lights, modern lights, whether they're LED or light bulbs, they have sections of lights that are in series, but those sections are then connected in parallel. Okay, and that's why I said old lights, all of them are in series. Modern lights, you have multiple sections. Those sections are connected in parallel. So even if one section goes out, even if one light bulb in a section goes out, it only affects the light bulbs in those sections. So maybe you have 50 lights, for example. Let's say you have 50 lights, and they are broken down in sections of 10 light bulbs each. So one light bulb goes out, it only affects the rest of the 9 in there. The other 40 will still keep on working. Anyone ever seen that? Right? Modern lights, one light bulb goes out, only a certain amount of bulbs are affected. The rest still keep on working. And that's an example of a series and parallel connection. Okay, series and parallel connection. So if we take a look at our example here, what can we say about the elements A and B? A and B are in parallel. It may be quite obvious to some of you. For some of you, it might take a few seconds to take a look at it. But my goal, again, in recapping this, is that every student should be able to recognize and analyze this quickly. When I say quickly, I mean like within a few seconds, like less than 10 seconds, and you should be able to correctly determine which elements are in series and which are in parallel so that you can reduce it. So at this beginning, we go step by step. Always start at the farthest ends of the circuit schematic. So the farthest end here is A and B. Well, this dot that you see, by the way, simply notifies an electrical connection or a node. Some authors like to use it, some don't. So oftentimes you might see something like this, or you might see something like this without without a marking in there, without a node, without a dot. It still signifies a connection, an electrical connection. Okay, it's simply a node. 3-terminal node and 4-terminal node. Anyway, A and B are in parallel, and we can say the same thing about D, E, and F. Right? D, E, and F. So I could reduce this to one element. I'll call it, you can call it anything you want. I just call it AB. Whether the element is a resistor or a capacitor or an inductor, if it's in parallel or in series, you can reduce it to one single equivalent resistance, equivalent capacitance, and equivalent inductance. Okay, you can reduce it. Now, physically, of course, there are 2 separate elements or 3 separate elements, but electrically speaking, the circuit sees them as one. And so mathematically, we can analyze, and mathematically, we can reduce it to one single value or one single number. One, 2, 3, and 4. This is D, E, and F. So we reduced A and B to one element. We reduced D, E, and F to one element. The reason I'm saying take it step by step is because students often make an error when they do not. And so they would end up with the wrong or incorrect answer. Now, what can we say about C with relative to the rest of the elements? They're all in series, right? Most common mistake happens right here because you have 3 connections here, you have 3 connections here, and you have 4 here and 4 here. If it's not quite obvious, you would say, how can they be in series and in parallel? That is true. The relationship between A and C and between B and C, or C and with any element so far, is nothing. It's not in series and it's not in parallel. But the parallel combination of A, B is in series with C. And the parallel combination of D, E, and F is in series with C. Individually, these elements have no relationship with C in terms of series or parallel. Okay. Individually, they are not in series, they're not in parallel. They're just connected together. But collectively together, A and B together is in series with C, and D, E, and F together is in series with C. So you have to keep that in mind. Again, step by step. The first step is to combine everything that you see in parallel together and everything that you see in series together. If your first step is incorrect, the rest of your problem or analysis will be incorrect. Okay. All right. Any questions? Okay, moving on. Oh, this was assigned as practice. Don't know why I didn't note it down here. KVL. KVL, again, like KCL, is derived from the law of conservation of energy. It's actually quite brilliant. Current is kind of like obvious. You would say that all currents entering a junction have to leave a junction, or the sum of currents around a node is equal to 0. Similarly, KVL states that if you take an electrical loop, which is a closed pathway, and you sum up all of the voltages around that loop, they will always sum up to 0. Okay, they will always sum up to 0. So in this case, the first thing we do is we identify the loops. I always like to start at the bottom left corner of a schematic. You can start at any point, okay, any junction or any node in a circuit. I always start at the bottom left corner. So if I start at the bottom left corner, I want to identify all the loops in there. Goal is to start from this corner and come back to that same point. So I get loop 1. I can also start at the same place and go around the outer loop. In this case, it's marked as loop 3. Then I have this junction right here. I go around there and I get another loop. Any other loops in the circuit? You can go counterclockwise, you can go clockwise, you can start at the top, you can start at the right, you can start at the bottom. Doesn't really matter where you start from. As long as you come back to the same starting point, you will end up with the exact same loop. Okay. Now, you've done this before. This is probably familiar to you. If you have a technique of summing up the voltages and applying KVL, feel free to stick with that technique. You do not have to learn or follow what I show you in just a few minutes. Okay. Everyone has a preferred technique of applying KVL. So if you have that, you can stick with it. The way I do it is this. The sum of all voltages in a loop is equal to 0. So for loop 1, I have 3 voltages in loop 1, VA, VB, and VC. They should all sum up to 0, right? So I have VA, VB, and VC summing up to 0. I start at the bottom left corner and I go clockwise. That is just my preferred method. That's what I always do. I've been doing that for 30 years. So I always stick with what I'm comfortable with. You are free to stick with what you are comfortable with. Okay. Again, remember, this is not the method. This is just the technique of applying that method. If I ask you to solve it using KVL, then you need to show me you can apply KVL. But how you apply it is up to you. So you start at the bottom left corner and you start driving around the block. The first voltage I encounter is VA. VA has a minus and a plus, right? But first, if I'm driving in a clockwise direction, the first polarity I encounter for VA is minus. I'm going to put down minus VA. Next, I encounter VB, would be a plus. So that's a plus. And then continuing my path down the loop, VC I encounter is a plus. So plus VC equals 0. That's it. I have my equation. So the way I apply it, first step, identify the loops, identify all the voltages, write down all the voltages, I sum it up to 0, and then I go around the block driving my car. Whichever polarity I encounter first for every voltage is the plus or minus sign I note down in the equation. And it works whether you go clockwise, whether you go counterclockwise. Doesn't matter the polarity of the voltage, doesn't matter which point you start with, you will always end up with the exact same equation. If I was to start for loop 1, if I was to start at this node right here in the middle, okay, in the middle, I would still have 3 voltages, right? VA, VB, and VC equals 0. And for this time, let's say I go counterclockwise from this top node right here. If I go counterclockwise, I get VB first. VB is minus. Then I get VA. VA is plus. Then I get VC, also minus. The exact same equation, no difference. So this is starting from the bottom left corner. The first equation is starting from the bottom left corner. And going clockwise. This is starting from the top middle and going counterclockwise. You still have the exact same equation. No difference. The reason we take this slow is because you're going to take KCL and KVL and apply it to derive equations for larger analysis methods in the next chapter. So again, students need to be proficient at applying KCL and KVL quickly and correctly. All right, any questions? So I have problems here. I'm going to assign as practice. If you have any issues or you can't come up with the right answer, you let me know and we'll solve it. That is the end of chapter 1. Then let's move on to chapter 2. Resistive circuit analysis. And the first topic there is resistors in series. We just talked about how you can combine mathematically, you can combine resistors, capacitors, and inductors in series and parallel and reduce them down to one single resistance. So in this circuit example, we have 3. We have R1, R1, R2, and R3. And junction right here. You can see at those junctions, R1 and R2 are the only 2 connections. And so they are in series. And then R2 and R3 are also connected via only one junction. And so they also are in series. And hence we can say all 3 of them are in series. And the total resistance is measured at the outer terminals. That resistance is known as REQ, or the total equivalent resistance of that series network. Okay. The derivation is pretty simple. You're applying a voltage V to that circuit. So when you apply voltage V, it splits. You get VR1, VR2, VR3. When you apply a voltage, it causes a current to flow through the circuit. That current only has one path to flow through. It cannot go anywhere else. If it goes through R1, it has to go through R2 as well as R3 and return back to the circuit. There's no other pathway for it to go through, right? So the same current I flows in the circuit for all 3 resistors. Apply Ohm's law, I can get voltage V as the product of the current I and the total equivalent resistance REQ. VR1 is I times R1, VR2 is I times R2, and VR3 is I times R3. Take I outside, it cancels out. And you get REQ is R1 plus R2 plus R3. The derivation is not important. I don't expect students to memorize this. I don't expect you to, write it out step by step. As long as you understand it, and as long as you know the resistors in series simply sum up or add up. So the total equivalent resistance for REQ is R1 plus R2 plus R3. You could have 1,000,000 resistors all connected in series. The total equivalent resistance would be the sum of all those 1,000,000 resistors. Easy enough, right? Then, any questions before I move on? Resistors in parallel, derivation is kind of the same. You are all probably familiar with this. REQ for a parallel network is the reciprocal of the sum of all the reciprocals of the resistances. Quite a mouthful. But again, derivation concept remains the same. If you apply voltage V to a parallel network of resistors, in this case, in this example, it's 3, R1, R2, and R3. Now, because it's parallel, the voltage remains the same because it's the same exact node. The current, however, gets divided into I1, I2, and I3. if I write an equation from Ohm's law, I would be equal to V over Req. And I is equal to I1 plus I2 plus I3. So V over Req is equal to V1 or VR1 divided by R1 plus V2 divided by R2 plus V3 divided by R3. You solve this equation and you would get 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Because it's a parallel connection, voltage V1, V2, and V3 for all the three resistors is voltage V. V, 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 V. Parallel connection, voltage remains the same, right? So V cancels out. All you're left with is the resistance, and hence Req is the reciprocal of the sum of all the reciprocals. All right, questions? And again, as I said, derivation is not important. I don't expect you to memorize it, but I do expect you to remember the end result and be able to apply. More importantly, be able to apply. You can have this on your equation sheet. That is absolutely fine for series and parallel connections. Req equations can be on the equation sheet, but you should be able to understand and apply it when needed. Okay, that is more important. These are all tools in your toolbox. Okay, how to analyze circuits, how to reduce elements, and you need to understand how to use these tools. Okay. All right, any questions? So we'll end class here today. I will see you all tomorrow. Check Pearson and check Canvas for homework due dates. I think there was some confusion, so I extended homework 2 up to today. There should be KCL or KVL due tomorrow, I believe, and then on the 18th, 17th or the 18th. So again, check your calendars on Pearson as well as on Canvas. All right, we'll see you tomorrow.